Definitions. So this is a big finale for this chapter, and I think it's one that's going to be the most useful going forward. So the key thing is, with all mathematics, if you ever do any proofs in anything, you have to know your definition. You have to know what you're talking about. You have to know what's going on. So when they say it's something's a rational or even an odd number, if you don't know what it is, then you're going to be out of luck. So the key to making math easy is know your stuff. So here's some clearly defined terms that are going to help us through this lesson. When I say a rational number, rational numbers are numbers that can be fractions. So we just consider rational numbers stuff like this. That's a rational number. So if you could write anything in a fraction form, where the letters are integers, then you proved something is a rational number. So they're like, hey, show this is a rational number. You're just trying to make it a fraction where both of these guys are not decimals. And then you show it's a rational number. If you want to show something that's even, an even number could be is like the definition of an even number means you can divide it by 2. So how you show something that's even, you show it's 2 times something. Or in general, if they say, hey, we have an even number, you just show 2 times something. That's an even number. So when I say even number, it's 2 times something. Likewise, when you say an odd number, a noun number is 2 times something plus 1. You get that even number, you add 1 to it. You can also put minus 1 if you want. That's an odd number. So even number is 2 times something. A odd number is 2 times something plus 1. If you could show that something is that, you have an even number. So if you get something like x squared plus 2x minus 1, I'm like, even or odd? I have no idea. But if you had this, oh, that's an even number. Because no matter what this is, when you times it by 2, it makes it even. And if you add a 1 plus 1 on the outside, oh, now it's an odd number. So that's the general idea of even and odd. Now we're going to use that. We're going to use those and some other things to solve some questions. So first one here, we're going to prove that 0.13 repeating is a rational number. Now repeating numbers are rational numbers. We want to show you that's a rational number. So it means I got to make it a fraction. Oops. It would prove 0.13 equals some type of fraction P over Q. So that's what we got to show. Now there's a little bit of a trick to this. So what we're going to do is start here. I'm going to let x equal 0.13 with the line over it. Now, a lot of times it helps if you just write out what that means, right? So in this case, x equals 0.13, 13, 13, 13, 13, dot, 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 dot. Now, there's a little bit of trick to how we're going to solve at this, how we're going to make this a fraction. And that is, we're going to multiply both sides by 10 to some factor. Like, it depends how many zeros you have. So in this case, you have two things, how many places behind the decimal places repeat. So in this case, we have 2 things repeating, so I'll multiply both sides by 100. If it was only 1 thing repeating, then you multiply both sides by 10. If it was like something like 314 was repeating, then you multiply it by 1,000. Right? The number of times you have things you have repeating, that's how many zeros you add. So in this case, we're going to multiply both sides by 100. So multiply the left side and the right side by 100, right? It's an equivalent thing, so we're proving it by equivalence. Nothing's changing, and just multiplying both sides by 100. Again, the reason I chose 100, because there's 2 things being repeated, so I have 2 zeros. So I get this. 100x equals, what happens when I multiply this side by 100? You move the decimal place over 2 spots, and I get this. Dot, 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 right? So this is this guy multiplied by 100. And then what we're going to do here is this. We're going to rewrite this guy down below. Oops, let me line it up a little nicer, so it makes more sense. Right? That's what x is. X is 0.13. The line over it, so it's 0.13 dot dot dot. And what we're going to do now is just subtract them. Minus this side, minus this side. We have 100x minus 1x, so that gives us 99x. Over here, 13 minus 13.13 minus 0.13. All these cancel with all these, so you're left with only 13. Divide by 99, and x equals 13 over 99. And you just prove that the 0.13 is in the rational numbers because you wrote it as a fraction, so that means that 0.13 thus is an element of the rationals. Right? Because as long as you can write it as a fraction where these are not decimals, it's a rational number. And that's the whole idea. You just got to show, okay, could I rewrite that as a fraction without decimals? And that's how you rewrite a repeating number as a fraction. Let's move on. Prove that the sum of any 2 rational numbers is a rational number. So we're saying, hey, you add any 2 rational numbers, do you get a rational number? So let's start with that part. Any two rational numbers, right? So we're going to let one rational number be p over q. And let's let another rational number be a over b. Right? Those are my two rational numbers, p and q, a over b. Those are what rational numbers are. And what do they want? They want the sum. So let's add them. So the sum of p over q and a over b would be this. P over q plus a over b. And then I'm adding two fractions, so what do? You do a common denominator, right? So this side is missing the b, so multiply this by b over b. This side is missing the q, so multiply by q over q. And we get, I'm going to show all the work here, bp over bq plus aq over bq. How do you add fractions, right? You just add the numerators, and you get bp plus aq over bq. And then that's it. You show that this is a fraction, right? That's what a rational number is. It's a fraction. So you show that when you added these two things, you get a fraction. So that's a rational number. So if you were going to write it nicely, I would say b over q plus a over b equals bp plus aq over bq. So the sum of two rational numbers is a rational number. And there you go with that one. Let's do one more. Some one we did earlier. A is even, show that a squared is even. I think I talked about this before. Like that's the thing where like it sounded like it was correct, right? Like, oh, 2 squared is 4, 6 squared is 36. That sounds correct. Let's prove it now. Now that we have a little more skill. So a is even. So I'm just gonna write it as an even number. So 2k. Remember, an even number is just 2 times any number. So 2 times k is fine. When I say even number, you want to think 2 times k. If I said odd, 2 times k plus 1. Right, so this is an even number. And what do we want to show? That when you square it, it's even. Well, let's square it. When I square it, I get 4k squared. Now, that's not an even number. Right? An even number is 2 times something. So all we have to do here is rewrite it. This is the same thing as 2 times 2k squared. And that's an even number. Right? You don't have, as long as you don't have to factor out the 4, an even number is 2 times something. So if you can factor out 2 from it, it makes it an even number. So we got 2k squared. We squared it. We got 4k squared. I factored out the 2 to show that, hey, this is an even number. Right? 2 times something is an even number. So x squared is even. That's the idea. So I'm going to write it nicer, though. Let x, we're trying to show that x is an even number, equal 2k. Then x squared would equal 2k squared, which equals 4k squared. And that will show which equals 2 times 2k squared. Thus, x squared is an even number. QED. And that's the idea.